Hello everyone, this is the beginning of 7th week, the first lecture in week 7. In the past 6 weeks we have learnt several algorithms for solving unconstrained optimization problem. We learnt about gradient descent method, conjugate gradient method, Fletcher-Reeves, Newton's method, and a few different quasi-Newton methods. So, from this week onwards we will be moving to constrained optimization. So, we will be using certain algorithms that we have learnt from unconstrained optimization, but you need to recall that the way we will proceed with the algorithms for constrained optimization problem will have a lot of differences from the way we approached unconstrained optimization problem. Okay. So, yeah, let us get started. So, this is as I just mentioned, we will start with constrained optimization. So, yeah, as I just mentioned, we will start with constrained optimization. Recall the definition of a constrained optimization. Okay. So, we will minimize f of x where x is the choice variable subject to the condition that x is belonging to some set S, and so yeah, x belongs to some constrained set S. Constrained optimization problem is minimizing f of x over x, x is the choice variable, such that x belongs to some constrained set S, and this S should not be R n. Okay. So, if S is equal to R n, then yeah, it is an unconstrained optimization problem. If S is a strict subset of R n, okay. So, in that case, yeah, we call the optimization problem constrained. So, this is something that we have learnt in the first week itself, right. And yeah, so how do we find the critical point of a constrained optimization problem? No, before that, so we do not consider every possible constrained optimization problem. So, we assume a structure for the constrained optimization problem, and the structure is as follows. So, yeah, the structure of the optimization problem that we assume is min over f of x subject to the condition that g I of x is less than or equal to 0 for all I equal to 1 to p, and h j of x equal to 0 for all j equal to 1 to m. Okay. So, you can see that the constraint set is actually represented by p inequality constraints and m equality constraints, right. So, every I mean any constraint set that can be represented using these kind of constraints is what we are going to consider in this course. I mean, this was something that I mentioned many weeks back. You can yes. So, we gave this I think in the very first week of this course, right. So, yeah. So, we consider constrained optimization problem that has this structure. The constraint set S must be representable by a bunch of inequality constraints and a bunch of equality constraints. If it cannot be represented that way, then yeah, it does not fall in our purview. Okay. So, keep that in mind. And so, what is the critical point of this particular problem? So, it is a point that satisfies the following set of conditions. So, we write the Lagrangian function L of x lambda mu. So, which is given as f of x plus summation lambda I j of x I equal to 1 to p plus summation mu j I j of x j equal to 1 to m. Now, see the first condition is that the gradient of L over x must be equal to 0. So, that means del f of x star plus summation lambda I star j of x star plus summation mu j star of I j of x star must be equal to 0. Okay. So, sorry, I should have written the gradient. Yeah. So, this condition must be satisfied, and other than that the equality constraints must hold, and as far as inequality constraints, we have a few more constraints that need to hold, which is g I of x star of course must be less than or equal to 0, but other than that you need lambda I star g I of x star equal to 0 and lambda I of x lambda I star must be greater than or equal to 0, and this must hold for all I equal to 1 to p. Okay. So, you can recall that this the set of x star lambda star mu star that satisfies these conditions. So, they are said to satisfy what we call as the Karish-Kuntaker conditions or KKT conditions, right. So, any set of x star lambda star mu star that satisfies the set of conditions are called the critical points. So, these set of conditions are called as the Karish-Kuntaker or the KKT conditions, and this is something that again that we looked at quite early in this course in the first week itself, right. So, I have just repeated what we have boxed here. Okay. All right. So, fine. So, this is I think a very brief recap of what constraint optimization means. Okay. So, this is how you find the critical points of a given constraint optimization problem analytically. Okay. So, if you can find this analytically, so you should be asking why are we actually working out the algorithms, right. So, again we gave two reasons in when we started with optimization algorithms for constraint optimization, sorry, unconstrained optimization, right. We can write down the two conditions here as well. Okay. So, one of the conditions is that one of the reasons is that the problem could be analytically intractable, maybe analytically intractable. Okay. So, as an example consider so f of x is or I mean let us consider the following problem: min x1 e power x2 plus x2 e power x1, okay, with respect to x1 x2, subject to the condition that x1 squared plus x2 squared equal to 1. Okay. So, I mean, so if you want to find the minimum, you will actually write down the KKT conditions, which means so you first write down L, which is x1 e power x2 plus x2 e power x1 plus lambda into x1 squared plus x2 squared minus 1, right, and the gradient with respect to x will be e power x2 plus x2 e power x1 plus 2 lambda x1 should be equal to 0, and similarly e power x1 plus x1 e power x2 plus 2 lambda x2 equal to 0, and x 1 squared plus x 2 squared is equal to 1. Okay. So, you have to find x 1, x 2 and lambda that satisfies all these 3 conditions simultaneously. Okay. So, just by looking at the equations you can see that analytically you can never find the ordered pair x 1 x 2 lambda that satisfies all 3 conditions, right. So, you need to use iterative methods, right. So, yeah, again this is very similar to again what we discussed in the beginning of week 3, right. So, yeah, I have mentioned these 2 reasons, analytically intractable problems. I have in fact given the same example, but which is unconstrained, right. And yeah, so there is this second reason as well. Here again I have actually given constrained optimization problem. So, if you want me to recall, so this is actually the optimization problem that you will be solving in SVM, which is the support vector machines. Okay. So, suppose you are given the data x 1 y 1 x 2 y 2 x and y n. So, this is a labeled data where for x you pick n values in RP, okay, and you label them either minus 1 or plus 1, and let us say that I mean the data is separable, okay, the set of minus 1 and set of plus 1s are separable. Okay. So, in such a case you will actually be solving this particular problem where you minimize half norm w squared subject to y I into w transpose x I plus b greater than or equal to 1 for all I equal to 1 to n. So, if you consider the data set, the number of data points will be like in thousands, and the number of feature vectors, that is p, will be yeah, in tens or hundreds maybe. Okay. So, what does it mean? It means that in this problem the dimension of optimizing variables or the number of constraints, either the number dimension of optimizing variable or the number of constraints are very large. Okay. So, in this case the number of constraints is n is, like as I said, it will run in thousands, sometimes in millions. Okay. So, in that case solving analytically seems meaningless, right. So, I mean these are the settings where we actually go to solving the problem using computers. I mean we want to outsource all of these jobs to a computer, right. So, that is the reason. So, we have 2 reasons now, that is analytically intractable and dimension of optimizing variable or constraints are very large. Okay. So, based on these reasons we will actually try and work on coming up with algorithms for constraint optimization. Yeah. So, before starting with an algorithm I would like to consider or rather let you know about 2 major classification of constraint optimization problem. Okay. So, one is called as the linear programming or linear optimization problem, and the other obviously a non-linear optimization problem or non-linear programming. Okay. So, yeah. So, when do you call a constraint optimization problem linear? So, you call it linear if f of x is of the form C transpose x, in other words it is linear in x, okay. And g I of x are of the form A I transpose x minus b I, okay, and h j of x are of the form A j bar transpose x minus b j bar. Okay. So, bar is just to differentiate that one is the inequality constraint and the other is the equality constraint. Okay. So, that is a linear optimization problem will always be of this form, okay, min C transpose x subject to A transpose x minus b I less than or equal to 0 for all I equal to 1 to p, and A I bar transpose x minus b I bar equal to 0 for all A j bar Bj bar for all j equal to 1 to m. So, whenever you have an optimization problem of this form, then such an optimization problem is called as linear optimization problem. So, putting it in a nutshell, the objective function, the inequality constraint equation, the equality constraint equation, all of them must be linear in X. If that happens, then yeah, the optimization problem is linear programming or linear optimization problem. Okay. Yeah, linear programming is the word that is often used, and I mean in short we call it as LP. Okay. So, even if one of them is nonlinear, either the objective function is nonlinear or one of the inequality constraints is nonlinear or even one of the equality constraints is nonlinear, then the problem is actually called as nonlinear programming or nonlinear optimization problem. Okay. So, the reason why this classification exists is that when the optimization problem is linear, there are some very nice ways of solving the problem. I mean there is a lot of structure into the solutions that we can say for linear programming problem. Okay. And the second reason is that the algorithms that work for linear programming do not work for nonlinear programming and the vice versa. Okay. So, you need to use two different kinds of algorithms for solving linear and nonlinear optimization problems. Okay. So, that is the reason why we are actually hell bent on letting you know about these different kinds of problems, the linear and the nonlinear programming problems. So, we will first start with nonlinear programming problems. So, nonlinear programming is yeah, at least when one of them is nonlinear. Okay. So, and we will look at two algorithms, one is called as the quadratic penalty method and the other is augmented Lagrangian method. Okay. And then yeah, in the later weeks we will actually move to the algorithms for linear programming. Okay. So, yeah, I mean this could be a change in order based on if you look at the syllabus what was mentioned initially. Okay. But I think that is still fine. Okay. All right. So, as I mentioned, yeah, F, GIs and HJs are all linear. So, that is for linear programming. So, for nonlinear, at least one of F, GIs, HJs is nonlinear. And we are going to start with nonlinear optimization problems or nonlinear programming. Okay. So, when I started this lecture I mentioned that for constrained optimization, for unconstrained optimization we had a very nice method, right. So, we start with a point, we figure out the descent direction and the step size, move there, figure out the descent direction step size again, move over there, keep doing that until we satisfy a stopping criterion. So, this was the basis for every unconstrained optimization algorithm that we have learnt, right. So, in constrained optimization that does not work. Okay. I mean it is not at least it is not a very simple extension of the constrained optimization algorithms. Okay. So, what is the reason? So, I mean I will just start with a simple example. Okay. So, yeah, let us consider this particular problem where yeah, you are minimizing x1 plus x2 subject to the condition that x1 squared plus x2 squared minus 1 equal to 0. So, yeah, over x1 x2. So, what this means is that, so you have a unit circle and yes, you should find the point on the boundary of this unit circle in such a way that x 1 plus x 2 is minimized. So, yeah, if you had worked out sufficient number of problems like this, you would have immediately figured out that the answer is minus 1 by root 2 minus 1 by root 2. Okay, so, yeah, if you square them and add it, it is equal to 1. So, yeah, it falls on the unit circle, and that is what minimizes x 1 plus x 2. And yeah, if you want to use the KKT conditions, that is also fine. I mean, you write L as x 1 plus x 2 plus lambda into x 1 squared plus x 2 squared minus 1, and yeah, so if you differentiate with respect to x 1, you have 1 plus 2 lambda x 1 equal to 0, which means yeah, x 1 is minus 1 by 2 lambda, and when you differentiate with respect to x 2, you have 1 plus 2 lambda x 2 equal to 0, which means x 2 is minus 1 by 2 lambda as well. So, x 1 squared plus x 2 squared equal to 1 implies 1 by 4 lambda squared plus 1 by 4 lambda squared. So, 1 by 2 lambda squared equal to 1. So, lambda is plus or minus 1 by root 2. Therefore, x 1 equal to x 2 equals plus or minus 1 by root 2. So, that is because lambda 2 lambda is plus or minus root 2. So, that is minus 1 by plus or minus root 2, which is just plus or minus 1 by root 2. Okay. So, so of course, it gives two critical points. One of them is 1 by root 2 1 by root 2, and the other is minus 1 by root 2 minus 1 by root 2, right. So, you can check the second order conditions to figure out that this critical point corresponds to the maximum and this corresponds to the minimum. Okay. So, I am not going to do it here. So, now coming to figuring out an algorithm. Okay. So, why not use the same kind of algorithm that we used for unconstrained optimization? I mean, that is, start with a point, I mean, find out just the direction and step size and keep moving ahead. So, the problem is clearly the constraint set, right. So, suppose I start with a particular point, say yeah, somewhere I start here, and with a particular direction and step size I move here. I have already moved outside the constraint set, right. So, it is not clear if I mean how to use the constraint equation so as to get back to the constraint set, right. So, I mean here the constraint set is visible. So, if you take higher dimensional problem, say 5 dimensional problem where you are searching over x 1, x 2, x 3, x 4 and x 5, you do not have a nice figure to figure out where you are, if you can come back and so on. I mean those are much difficult things to do, right. So, yeah, you need to somehow accommodate the constraint that you are having, say the gi of x, hj of x and all that, in such a way that yeah, you have some possibility of using this technique of just finding out the direction and step size, if at all possible, right. So, one way is the following. Okay. So, let us say if so let me actually define a function called q tilde of x, okay, where q tilde of x is f of x if x is in the constraint set, and it is infinity when x is not in the constraint set. Okay. So, let us assume that I mean I am just giving you a way to get way to accommodate the constraint set somehow. Okay. So, suppose I do this. Okay. So, this is nice because now if I mean, so I claim that, I mean, yeah, I mean, I think it is easy to see that this problem where you minimize f of x subject to x in S is actually equivalent to minimize q of x unconstrained, that is x in Rn, sorry, q tilde of x. Okay. Of course, I mean, there is nothing great about this, because if it is in S, it is f of x, otherwise it is infinity. So, if you move out of S, you are certainly not going to get the minimum, right. So, both of these problems are equivalent, but what is the problem? The problem lies in the differentiability of q tilde of x. Okay. So, if I mean, so we were able to use all the algorithms for minimizing f of x, right. So, all the algorithms that we had considered for minimizing unconstrained optimization, we had assumed f to be twice differentiable, not just differentiable, we wanted it to be twice differentiable, right. So, if q tilde of x is like what I have defined here, f of x is when it is x in S and infinity when x not in S, obviously this function is not differentiable, right. So, I want to have a function which is differentiable, at least differentiable if not twice differentiable. Okay. So, that yeah, I mean, I can use the algorithms that I mean we discussed for unconstrained optimization, right. So, how do we convert this into a tractable function or a smooth function, so that we can use the algorithms that we use for unconstrained optimization. So, we will see that in the next lecture.